Hello everyone and welcome to Robot Operating System version 2 or ROS2 Jazzy tutorials. In this ROS2 tutorial, we explain how to correctly import external CAD geometry of a robot, and we explain how to write a package that will correctly visualize and simulate this geometry in ROS2 Jazzy and RViz. Over here, you can see the simulated geometry of a robot. The robot consists of 4 links: the base link, the first link, the second link, and the third link. Also, links are connected by joints. Here is the first joint, and over here you can see the slider that enables us to move the joint. The second joint is located over here, and you can see as we move the slider, the second joint moves, and the third joint is located over here, and this slider enables us to move the joint. This robot has 3 degrees of freedom. However, everything explained in this video tutorial can be straightforwardly generalized to robot with 6 or more degrees of freedom. The original geometry is created in FreeCAD, and over here you can see the assembly. Namely, the assembly perfectly matches the robot simulation in RViz. And over here you can see the parts. This is the base, this is the first link, this is the second link, and this is the third link. We have created a separate video tutorial explaining how to create this CAD geometry in FreeCAD, and a link will be posted in the description below this video tutorial. Once we have created this geometry, we saved every part separately as a collada file, that is as a file with the extension DAE, and then later on we wrote a URDF file, which you can see over here, that imports and simulates this geometry in RViz. Besides this URDF file, there is a separate launch file and a bunch of other files that enables us to simulate this geometry. We are going to explain how to write everything from scratch. On the other hand, as mentioned previously, we are not going to explain how to model this geometry in FreeCAD. For that purpose, watch another video tutorial whose link is given in the description below. Here is the Python file that's used to visualize and to simulate the geometry in RViz and ROS2. In this video tutorial, we will explain how to write this Python file as well as the URDF file and a complete package. Besides these files, we have created a detailed manual explaining all the steps that need to be performed in order to implement the package and to visualize the geometry. Here is the file. A link to this file, to the Python file, URDF file, CAD files, as well as to all the files explained and developed in this video tutorial will be given in the description below this video. Okay, let's start with explanations. In this ROS2 Jazzy tutorial, we explain: number 1, how to import an external robot 3D CAD geometry from a CAD file into ROS2. Number 2, how to create a minimal unified robot description format or URDF file format and a model displaying the CAD model. Number 3, how to create a ROS2 Jazzy package and a launch file for visualizing the CAD model. And number 4, how to visualize the robot geometry in RViz and ROS2 Jazzy Jalisco. Before we continue with explanations, let's explain the basic terms, since a lot of viewers of this channel are completely new to ROS2 or completely new to robotics and they don't know what is URDF or XML file. First of all, what is a URDF file? URDF file format is a widely used XML file format for describing the geometry and configuration of robots. It's used in ROS and Gazebo to define the geometry, joints, and configuration of robots. On the other hand, RViz is a 3D visualization tool, as well as way more than that for ROS2. It's a light version of Gazebo. Although RViz doesn't simulate the dynamics and Gazebo simulates the complete dynamics. Then let's explain what are the launch files. Launch files are ROS2 files that are used to configure and run at the same time a number of ROS2 nodes and other components of a ROS2 system. For example, with a single launch file, you can run a number of different nodes and components for controlling a mobile robot. Here is the license and the copyright notice. This document, develop code files, lesson video, and all the provided material are referred to as the learning material in the sequel. Number 1. The learning material is the ownership and the original work of Dr. Alexander Haber, who is referred to as the author in the sequel. Number 2. You have the right to use the learning material for personal educational use and strictly for non-commercial use. Number 3. The learning material should not be copied, redistributed, or publicly posted on public or private websites, code repositories, and social media platforms. Number 4. The learning material should not be reproduced manually or automatically using an algorithm or an AI model from this video and then posted on public or private online repositories. Number 5. Unless allowed by the author, the learning material should not be used as official or unofficial lecture material on online learning platforms and in university courses. Number 6. Unless allowed by the author, the learning material should not be used to train engineers working in companies or paid academic researchers such as paid students, paid postdocs, and paid professors. Number 7. The provide coded files and learning materials should not be used to train an AI algorithm or a large language model. And number 8. Unless allowed by the author, the learning material should not be used in academic papers, student reports, engineering reports, or other related documents. Before we explain how to recreate this simulation from scratch and how to write the complete package, let's first briefly explain what's happening behind the scenes. Over here, you can see the graphical representation of nodes and topics that are running in the background. First of all, we have the joint state publisher graphics user interface. The graphics user interface of this node is given over here, and this graphics user interface can be used to set the angles of rotation of every joint. I can set joint 1, joint 2, joint 3. Then, this information is actually passed through the topic called joint states. Then, this information is received by another node called robot state publisher. You cannot see a graphics user interface of this node since it's running in the background. This node receives the information and uses the URDF model and kinematic chain to create a complete set of transformation and kind of to form everything. Then this information is sent through the topic TF to the transform listener, and RViz can read this information and can display this information graphically. That is, once I set these positions, or better to say angles of rotation, this graph will run and then it will communicate this information to RViz. RViz is going to use information from the topic TF as well as the URDF model, that is the CAD model of our system, and display and simulate everything graphically. And in this video tutorial, we are going to learn how to implement these nodes and these topics. In order to correctly understand everything explained in the sequel, it's very important to correctly define the state of each joint. The state of each joint is defined by, number 1, the position or the angle of rotation of the joint, number 2, the linear or angular velocity of that joint, and number 3, the force or torque that is applied to the joint. And let's explain first of all, number 1, the position or the angle of rotation of the joint. In the case of revolute joints, the component of the state is the angle of rotation, expressed in radians or briefly rad. In the case of prismatic joints, the state is the position of the joint, expressed in meters or briefly m. Then, the linear or angular velocity of the joint. In the case of revolute joints or rotational joints, the component of the state is the angular velocity in radians per second or briefly rad per second. In the case of prismatic joints, the component of the state is the linear velocity expressed in meters per second or briefly m over s. And number 3, the force or torque which are both referred to as the effort that is applied to the joint. In the case of revolute joint, the component of the state is the applied torque, expressed in Newton meters or briefly Nm. In the case of prismatic joints, the component of the state is the applied force to the joint, expressed in newtons or briefly N. Note that this definition of the state is different from the kinematic definition of the state, which takes into account the position or angle of rotation and velocity or angular velocity. For example, when you write a state space model, the states are kinematic states and forces or torques act as inputs, and this is the case in the classical control theory. On the other hand, in the case of ROS2, the state contains, again, the position or the angle of rotation, then the linear or angular velocity of the joint, and in addition it contains the force or torque. And this is very important to keep in mind. The state is communicated or published, or better to say, or in case of some other nodes, received by using the topic called joint states. You can obtain the information about this topic by typing this command, ROS topic info, and then the name of the topic, which in our case is joint state. And this will be explained later on in this tutorial after we create the model. Here are several important things to keep in mind. The state information is received by the node called robot state publisher. And that's precisely the node that we explained previously. This node receives the state information for every joint, and by using the URDF model of the robot, publishes 3D poses of the robot links using a kinematic tree of the robot. The node robot state publisher makes use of the URDF robot description defined by the parameter robot description and the joint position from the joint states to calculate the forward kinematics of the robot and publish the results to TF2 topic. That is, the state of the robot is published to TF2. This is very, very important to keep in mind. TF2 is a transform library. At the same time, this is the name of the topic that is used to keep track of the relationship between coordinate frames over time. It maintains a tree structure describing the relationship between the coordinate frames. Also, this library enables us to transform vectors, points, or any quantity between any two coordinate frames. Again, robot state publisher publishes 3D poses to TF, and this information is passed to transform listener node. Then the visualization of the robot motion can be shown in RViz. RViz is actually a node, however, it's not shown in the graph that we explained previously. As you will see later on, we will write a Python launch file that will start all these nodes at the same time. Okay. So let's start with implementation. And finally, let's start with implementation. First of all, let's start with the prerequisites, and let's double check that you have all the necessary components. To implement the material presented in this tutorial, you need to have, number 1, Linux Ubuntu 24.04. Do not use Windows subsystem for Linux or WSL since you might have issues displaying graphics. Install Linux Ubuntu on your computer. If you have a Windows computer, then you can easily install Linux Ubuntu in parallel to the Windows operating system by using a dual boot approach. Okay, to verify that you have the correct Linux Ubuntu version, click here, then search for terminal. And in the terminal, you need to write this command, lsb_release-a, and you should see your Ubuntu version. You should see Ubuntu 24.04. This last number really doesn't matter. These two numbers matter. Next, let's verify that ROS2 is installed on your computer. To implement the material presented in this tutorial, you need to have ROS2 Jazzy Jalisco. Let's verify that ROS2 Jazzy Jalisco is installed on your system. First of all, you can try to list the content of this folder, opt ROS Jazzy. This is a standard folder for installing ROS2 binaries. And if you see that this folder is non-empty, this means that most likely ROS2 Jazzy Jalisco is installed on your system. However, the best check is to actually try to run this setup file by executing this command. And if you don't see an error, that's a good sign. And finally, you can print the ROS distro environment variable, and if you see Jazzy, this means that ROS2 Jazzy Jalisco is properly installed on your system, and we can continue. The next step is to install the necessary ROS2 packages or verify that they are installed. In this tutorial, we will need several ROS2 packages that are most likely installed if you follow the official instructions for installing ROS2 Jazzy desktop version. However, it's still a good idea to try to install them. First of all, we will need the Joint State Publisher graphics user interface, then we will need the Robot State Publisher, and then we will need the RViz package. So I open here a new terminal, and since I did that, I again need to source the environment. Okay, after doing that, let's make sure that our system is up to date. Sudo apt update, and then after that you need to run sudo apt upgrade. This will update and upgrade everything on our system, that is all the packages. Enter your password and wait until this command is completed. My suggestion is to often, here press Y, my suggestion is to often run this command. Okay, and then let's install the necessary packages. Let's install Joint State Publisher graphics user interface. You can see that it's already installed, which is not surprising. And then let's install this Robot State Publisher. It's already installed. And finally, let's install the RViz package. And it's already installed. Good. Now, I will teach you one very useful command which can be used to locate the packages and to verify that packages are properly installed. The name of this command is ROS2 package list. This command will list all the ROS2 packages on our system. And you can see over here the list. It contains even maybe 100 packages. It's very difficult to go through this list if you're searching for a particular package. A better approach is to filter the results. Here, again, I'm calling ROS2 package list, and I'm directing the output of this command, and then I'm using this grep command to filter all the results that contain the word joint. And if you run this, you will see all the packages or the package name which contain the word joint. And here's the first one, and here's the second one. Let's do the same trick for RViz. So consequently, let's run this command, and you can see on top of the list RViz package. Good. Okay, the next step is to create the package, mesh, URDF, and launch files. So let's start. First of all, if you're starting from a new terminal, make sure that you source the environment so we can call all the commands. And then let's create the workspace folder. First of all, go to the home folder. And in the home folder, let's create two folders. This command will first construct or create a workspace folder called demo_ws, where WS stands for workspace. That's a standard convention in ROS2 community. And inside we will have this source folder, which will be created after created demo.ws. Okay, and then let's navigate to demo.ws, and inside you will see the source folder, and then let's navigate to the source folder. Inside of this folder, we need to initiate or create our empty package and to create all the files of the empty package. That is to create the file and folder structure. To do that, we need to execute this command. Let's explain this command. First of all, ROS2 package create is the command. Then over here, we are specifying with this parameter build type, a type of build that we want to perform. Here I'm using m and cmake. This means that I want to call the colcon build with C++. Note over here that I will not write a single line of C++ code. I'm just using the C++ build system. And finally, you need to specify the name of the package. The name of the package is demo_robot. And let's execute this command. And now several things happened. Scroll at the top and let's see what happened. Okay, creating folder, creating file, etc. So several files and folders are created, and you can type this and you can see that inside of the source folder a new folder is created, and this is our package folder. This package folder contains several files and folders. It contains a CMake list file. This is the CMake configuration file. We will edit this file later on. It contains an include folder. This folder can contain include header files, which we will not use in this tutorial. And then it contains package.xml. This is another configuration file that we will have to edit. And finally, it contains the source. This source folder contains the source files and folders of our package. Inside of this folder, we will create several folders. This is the command we will use. This command will at the same time create a launch folder, URDF, config, and mesh folder. And now if I type ls-la, I can see the new folder. So let's explain these folders. First of all, config file is a configuration folder that will be used to store the RViz configuration file that we will create later on. Then the launch folder will be used to store the Python launch file, which will run everything. That is, this file will run all the nodes at the same time. Then we have this mesh folder. The mesh folder will be used to store the exported CAD mesh in the form of the Collada files. Then we have the URDF folder, and the URDF folder will be used to store the URDF file. Okay, so let's start creating these files. To create the first URDF file, I'm going to use the Visual Studio Code. To start Visual Studio Code, navigate to the URDF folder and type code dot. If you don't have Visual Studio Code on your system, you have two options. Either you can use some other editor such as Nano or such as some other built-in Linux Ubuntu editor, or you can install Visual Studio Code on Linux Ubuntu by using the tutorial I created. You can find that tutorial on my YouTube channel. After running Visual Studio Code, let's create an empty file. Click on File, New File, and here it's very important that the file name is properly defined. Let me do it again, and let me paste the name of the file. The name of the file should be model.urdf. And press enter. Make sure that you save that file in the URDF folder. Here it is. Now, I'm going to start from scratch, and I'm going to write this URDF file step by step. I'm going to first add a single link. Then I will compile and build the package, and I will visualize that link. I'm doing this in order to explain all the coordinate systems and to explain step-by-step procedure. You don't need to do that. You can immediately write all the links and all the join descriptions, and then you can visualize. However, for clarity of this presentation, I will do it step by step. Okay, so first of all, here I prepared the first part of the code, and I'm going to paste this code. Now, let's explain what this code is actually doing. This code will actually load mesh file name. That is, it will load the external CAD geometry, and the external CAD geometry is defined over here. Okay, so let's create this file whose name is base_link. For that purpose, I'm going to go to AutoCAD, or not AutoCAD, FreeCAD in my case, and I loaded all the parts over here. Then I'm going to click on the base. This is my base part. That is, this is the first link of my robot system. And I'm going to click on File, and I'm going to export this. Okay, over here, if you expand, you can see different export options. I know that some people are also able to import, or to better to say, to export STL files. However, by following or after reading the ROS2 documentation, you can see that the suggested option for exporting files is Collada, which has the extension DAE. Consequently, over here from the list, I selected Collada. Again, some other file formats might work. Okay, so where do I need to export this file? Well, I need to go to my user folder, or better to say to my home folder, and then I need to find my workspace folder. Here it is, demo workspace, source, demo robot, and then I need to store it in the mesh folder. So click on the mesh, and let me for a second go back to my Visual Studio Code, and the name of the file should be base_link. So let's type the name, base_link. This is the convention for naming files. Now let's verify that this file actually exists. If I go to Home, Demo Workspace, Source, Package folder, and if I go to Mesh, you'll see the file over here, base_link DAE. Good. And now let's explain what is written over here. This is the XML file that's used to implement the URDF files. First of all, over here, you need to specify the version. Here it is. Then you need to specify, or actually this is actually the comment. This is how we write comments. Nothing special. You start the comment with this tag and you end the comment with this. Over here, we create the robot tag and we end the robot tag. And everything within the robot tag describes a robot. Here I'm specifying the name as simple robot. However, you can call it as you wish. Then I need to define a link. In URDF, robots consist of link and joins. Links are structural elements, such as base in our case, and joins are used to connect links and to enable relative motion of one link with respect to another. In practice, links can be actuators or similar mechatronics elements. Then inside of the link tag, note here that I started the link, its name is base link, and I close the link. And inside of this tag, I need to create a visual representation of my link. Then I start the geometry tag and I end the geometry tag, and over here I'm specifying the mesh file name. Note over here that I'm doing this with a single line, and let's explain what is written over here. This is actually the path to the DAE file, that is to our mesh file. Here, package stands for the package folder, right? So it's the package folder, so I will explain that later on. Then we have demo robot, then we have mesh and base link. So let's explain what is this package folder. The package folder is actually, or better to say, this path is being measured from here. Okay, so you can imagine that over here you actually have the absolute path. Instead of this is the absolute path to the source folder inside of our workspace folder. And then relative to this folder, you need to specify the path. And let's see. So it's demo robot. This is the name of the package. Then we have mesh. This is the name of the folder. And inside of the mesh, we have our base link. And here it is. This is the geometrical description. Then over here, you need to specify the coordinate system or the reference frame of that link. This is the frame attached to the link. And you need to specify the coordinate origin. X, Y, Z represents translation in the X, Y, and Z direction with respect to the reference or the world coordinate of RViz simulation. And by specifying translations to be 0, we are actually fixing this in the world coordinate system of the RViz simulation, and RPY represent the roll, pitch, and yaw Euler rotations. These are the rotations around X, Y, and Z axis of the world coordinate system. and we don't have any rotation, consequently we have 0, 0, 0, and we end the visual link, and that's it. And let's save this file. Okay, in the sequel, I'm going to build everything assuming that our robot consists only of this single link, and later on I'm going to add more links and explain the coordinate systems. Next, we need to create display.launch file. To do that, click on File, a new file, and call the file as display.launch.py. And it's very important that this file is actually a Python file. That's why this file ends up with display.launch. That is, it ends with py. Okay, so let's press enter and make sure that you save this file inside of the launch folder. So go back to this source folder and find the launch folder and save the file over there. And over here, to save time, I'm going to paste the content of the file. And let's explain what this file will actually do. First of all, we need to import the necessary libraries and packages. We import launch, then from launch substitutions we import command and launch configuration, then we import launch ROS, and we import ROS. First of all, we need to define the package name. This is the package name we just created. Then we need to specify a relative path to the URDF file with respect to the package path. The URDF file is inside of the URDF folder, and the name of the file is model.urdf. That's precisely this file, and this path is a relative path with respect to what? With respect to, let's find it, demo source, with respect to this folder, namely the URDF file is inside of the URDF folder. Good. Then we need to specify the name of the RViz configuration file and its path. We still didn't create the RViz configuration file. This file will be created first time we run everything, namely we are going to set up the RViz display, and then we are going to save the display configuration inside of this file in the folder config. This is the folder we just created. And over here we define a function that will run all the nodes. First of all, we need to retrieve the absolute model path. To do that, we call launch ROS.substitution.find package share. We specify the package name, and then over here we find the package name, and this will return us the absolute model path. That is the absolute path to our model. And over here we actually receive the absolute path to the URDF file. We simply combine package path with the URDF relative path, and to correct myself, this is actually the absolute path to the URDF model, defining all the configuration of our robot. Then over here we define the absolute RViz configuration file path. We use the same strategy. Here for model verification we print the URDF model file. This is for debugging. And then over here we load the robot description. To do that, we simply open the URDF model file. We open it in the read mode, and we simply store everything inside of our URDF file in this string, this huge string called robot description. Then we define this dictionary containing the robot URDF description. This will be used later on. And over here we define the robot state publisher node, and we explain how this node should be executed. We use the function launch.ROSActions. We call the node, we specify the package name, we specify the executable, where this thing will be published. We pass the parameters contain the URDF file, and over here we specify the URDF model path, and that's it. Then we need to create and start the joint state publisher node graphics user interface. We again use launch ROS actions node. We specify the name of the package, we specify the name of the executable, we specify the name, we pass as argument the path to the URDF file, and over here we are specifying condition. that we want to run with the graphics user interface. Then over here, we explain how the RViz node should be started. Again, we specify the package, executable, name, where the output will be, and the arguments. We specify the RViz configuration path. That is, this is the path to the RViz configuration file that will be created later on. And finally, we combine everything and we return. So we do return launch, then we call launch description, and we specify over here the launch arguments. Let's see what we specify here. We specify name should be graphics user interface, default value true, and here we specify description. This is the flag for joint state publisher graphics user interface. Then we specify that we want to run the robot state publisher node, joint state publisher node, and an RViz node. Note over here that I commented this part over here, as well as the definition of run properties of joint state publisher node. So let me explain one very important thing. If you run joint state publisher with the joint state publisher graphics user interface, there will be issues in ROS2 Jazzy Jalisco. This didn't happen in ROS2 Humble. However, in ROS2 Jazzy Jalisco, you can only start joint state publisher graphics user interface or joint state publisher. Joint state publisher performs the same task as the joint state publisher graphics user interface. However, it doesn't use graphics user interface. And that's why I commented this part over here. You don't need to type this and you don't need to type this. And that's it. You can simply type this file. Here again is the file from here to here, from here to here, and from here to here. Practice typing this file, or you can use the provided. Okay, make sure that you save this file and make sure that you save the model.urdf file. Next, we need to edit two files. They are package.xml and cmakelist.txt. Open these files. Let's start with package.xml. Click on File, open File. I didn't want that. Let me see File, Open File, and let's go to our package folder and let's start with package.xml. Okay, over here we need to add several lines. We need to tell to ROS system that our package actually depends on external packages. We need to add these 3 lines. So I will copy them and I will paste them over here. It really doesn't matter where you put these lines. However, don't put them outside of this package tag. So here they are, and let's explain what they are doing. First of all, here we are saying that our package depends on joint state publisher graphics user interface package as well as robot state publisher and RViz package. Save this file and let's edit the CMake file. Click on File, click on Open File, and let's find CMake lists. Open this file, and over here before if build testing we need to add several lines, and here are the lines. We need to install the necessary directories. What does it mean to install a necessary directory? Here we need to tell to the CMake build system that our source files are stored in newly created packages. Namely, when you write package create, a certain default folders will be created, and CMake system will look for files in these folders. If you create additional folders, then you need to tell to CMake system that these folders also contain source files, and you do it like this. You simply call install, then you call directory, and you specify the folder names. They are launch, URDF, config, and mesh. These are the new folders we created. And then over here, simply save this file and we can continue. The next step is to build the project. So go back to the original terminal and know that this terminal should be the terminal in which you were executing the source command which created an underlay. Okay, and then navigate back to the workspace folder. That is, you need to be in this folder. And this is very, very important when you build the package. Always build everything starting from the workspace folder. However, before we actually build everything, let's double check that all the packages and all the dependencies are installed. To do that, we need to install ROS2 by executing this command. Then let's initialize the ROS2. And then let's update the ROS2. You can simply ignore some errors if they appear, since they are not essential. And then finally, after we initialize ROS2 or an update, we can run this command to verify that everything is properly installed. And you should get this message, all required ROS2s installed successfully. And finally, we can build everything. To build everything, you need to call the colcon build command. That is, you need to call this command. Colcon build, then you need to specify symlink install, and then you need to select only a single package, and the name of the package is demo robot, and that's it. And now everything will be built. Hopefully there are no errors. And then let's run everything. To run everything, I'm going to open a new terminal. And then even in this terminal, you don't need to be in the workspace folder. However, to run the newly created package and the newly created nodes, you need to source the overlay. That is, this time you're actually sourcing not the base ROS2 environment, you're actually creating or actually sourcing and executing a configuration file inside of a newly created package. And you can see it over here, the path to this setup.bash file. So let's execute this, and now we can run the node. To run the nodes, or better to say, to run the launch file, we simply need to call ROS2 launch, then the name of the package and the name of the executable, in our case display.launch.py. Let's press enter and let's analyze what's written over here. Okay, first of all log files can be found below. Good. Then default logging verbosity is set to info, nothing special. Then here comes a very important information. Robot state publisher started, good. Joint state publisher started, good. RViz started, good. Robot initialized, centering, so no errors. This is very, very important. And once you open RViz, you will not see anything. Is this an error or not? Well, it's not an error. This is because we didn't create an RViz configuration file. We need to do several adjustments over here such that we can visualize the robot. Once we make these adjustments, we are going to save these adjustments in a configuration file, and the next time we start RViz, the robot will be immediately displayed. So let's start. Click on Add, and over here find Robot Model. Click on OK, and then you need to expand the robot model. First of all, here you will find the description source. Give it as topic, and description topic contains other useful information. To show the robot, over here you need to click on description topic and then on the drop down menu and click on robot description, and after you do that you will see that the base link is displayed here. However, something is not correct. The colors are not good. Namely, if you go back to the free CAD, you will see that the base link's color is red. So let's fix that. Go back to RViz, and over here, instead of map, type base underscore link. And after you press enter, the link will be properly displayed. So what's the catch over here? You need to assign the fixed frame. And this fixed frame is actually the fixed frame of the base link, and the name is base link. Okay, that's it. Now go back to RViz, and if you click here you will see this menu. However, there are no joints to be moved, and we need to add joints as well as other links. You can freely close RViz without saving anything. So close without saving, go back here to the terminal where you started RViz and press Ctrl+C to kill everything. The next step is to add additional joints and links. So go back to FreeCAD and let's analyze. This red CAD geometry is the base link. This green part is the first link. Between the base link and the first link we have a joint, and we need to model that joint as well as the first link. So let's do that. First of all, let's go back over here and let's click on the first link, then click on the file, and then click File and click on Export. And export this file to the corresponding folder. Make sure that you go to the Demo Robot Mesh folder that is inside of our package folder and inside of Mesh, and call the first link as first_link.dae and press enter, and now first link is being saved. Let's write the URDF file that will, or URDF piece of code that will model this link. I'm going to go back to the Visual Studio Code, and over here to save time I'm going to simply copy and paste the piece of code. Here it is. And let's paste this code and let's explain what this code is doing. Okay, over here we are defining our first joint. Going back to FreeCAD, this is the joint connecting first link and base. Okay, the type of the joint is revolute or rotational. And then we need to specify the parent link and the child link. So what is the parent link of this joint? Well, the parent link of this joint is the base link, and the child link is the first link. And that's precisely what we are typing here, base link and first link. Note over here that first link is defined in the sequel. And then over here we need to specify the origin of the first joint. So what is the origin of the first joint? Namely, with every joint, we associate a coordinate system. And we need to define the origin of that coordinate system. This coordinate system is defined with respect to the origin of the previous joint. Implicitly, the previous joint is attached to the base link. And consequently, the origin of the previous joint is actually the origin of the base link. And these coordinates over here define the origin as well as the orientation of the coordinate system of the first joint with respect to this fixed coordinate system associated with the base link. So let's see what are the offsets. First of all, if you go back to the CAD model, you can see over here that the joint, whose origin is actually located at the center of this cylinder over here, and its 0 point is actually on this plane over here. That is, its origin is at the top over here, at the center of this top face, of this circular top face, and we can see that this origin is displaced with respect to the origin that lives over here, and the displacement is in the z direction. And so let's see what is the displacement. This is 80. Note over here that I click here to get this distance, and this thing is also, oops, I didn't, let me now do distance. So the total one, actually this is not 200, let me reset this, and let me click over here. And let me do right click over here. No, this doesn't work. I have to reset, so I have to do it manually. So I have to click here and I have to measure. And let me reset now. This is sometimes confusing. Let me close this completely. And let me go back here. Okay, anyway, so this distance from here to here is actually, if you add them together, 0.16, since this is 0.8 as well as this thing is 0.8, and hopefully now it might work. Okay, so let's click here, and anyway, it doesn't work for the time being. Something is wrong. Okay, but the whole point over here, that since this is 0.08 and the other part is 0.08, you'll have 0.16 over here. And then you need to specify the axis of this joint. The axis of this joint is revolute around the z direction, and consequently over here you will have to specify 0, 0, 1. Note over here when defining the origin you have 0, 0, 0. This means that you don't have rotation of this coordinate system with respect to the coordinate system attached to the base link. And then you need to specify the effort. This is the maximum torque, this is the maximum velocity, and these are the lower and upper rotational limits expressed in radians. And that's it. Next, we need to define the first link. So what is the first link over here? Again, we start the link, we call it first link, we define visual, we end visual, and then over here we define geometry. We import this file over here. This is precisely the Collada file we just saved. We end the geometry and we define the center of the link. This is actually not the center of the link when you import the CAD geometry. This is actually the coordinate system. That's precisely this coordinate system defined over here. That is the coordinate system of the joint. This is just a convention when importing the CAD files. If you manually define your geometry over here, such as using boxes or using cylinders, then this coordinate system is located at the center of the link. To repeat, this coordinate system over here, and its offsets are 0, 0, 0, is precisely the coordinate system of this joint over here. Okay, so let's save this. Now go back to terminals, go back to the original terminal where you build everything and repeat the build command. Then go back to the second terminal that's used to run RViz. Source the environment once again. That is over here you're sourcing the setup.bash file of the package and launch ROS. And then over here let's repeat the procedure, add. Let's go back and add the robot model. Click here, then over here expand. Description topic should be basically robot description. Let's see what happens over here. Now you can see nicely two links over here, expand and select the base link, and everything works well. Now you can click here and then you can rotate the first link and everything works as it should. Next, let's add the second link and the third link and the corresponding joints. First of all, go back to the FreeCAD, then click on the second link, click over here, and let's export the second link. To export the second link, click on File, Export, and then over here, let's find the folder of our workspace. Here it is. Let's go to the source, let's go to the package folder, mesh, and over here, let's call the second link simply as second_link, and let's save it as a DAA file, and let's do the same thing for the third link. So click on the third link over here, and let's save the third link. Click on body, file, export, and let's save it as third link.dae, and that's it. Okay, next let's go back to the URDF file and let's add a piece of code that models the second and third links and the corresponding joints. Over here I'm going to copy and paste the content. Here it is, and I'm going to paste it over here, and I need to explain it. Okay, so let's see what's happening over here. Between the first link and the second link we have joint 2. Let's see where it is. Go back to the assembly, and here it is. So over here is the rotation joint. You can move that joint by simply clicking on assembly, and it's over here. So let's model it. How to model this joint? Well, this joint is of the type revolute. Parent link is the first link, child link is the second link, and let's define the origin. Note over here that this origin location is defined with respect to the origin of joint 1. That is, joint 2's origin is defined with respect to the coordinate frame associated with joint 1. And then let's see what happens over here. We don't have Euler rotations, however we have translations in the z direction for 0.24. This 0.24 is actually the distance from this plane to actually the axis that passes through the center of this joint. And here's the axis. You can see the cylinder over here, this one over here. So the center of this cylinder is a distance of 0.24 from here. And that's precisely what you can see over here. And then we need to specify the axis of rotation. Well, if you go back over here and if you see how the axes are oriented, the axis of rotation should be around the x-axis, as you can see over here. So we need to specify that. We specify the limit effort of 300 Newton meter, velocity, lower and upper limits of rotation in radians, and that's it. Next, we need to add the second link. We define visual. We define the file name. Here it is. It's a second link. And over here comes a very important thing. If you analyze this CAD geometry over here, we need to offset the coordinate system associated with this link with respect to the joint, and this has to go down for a certain amount. Namely, if I open up the second link, you will see over here this part. Let me now just rotate. Actually, it's here. I need to offset such that the center of this hole matches the center of the support cylinder. And that's precisely what's written over here. Next, we define the third joint. So let's see our geometry. Here it is. Here's the geometry. Here is the third joint. It passes through the cylinder supporting this link over here. That is the third link. You can see it partially over here. So the origin of that link is on the axis of this cylinder over here. You can see only a piece of cylinder here. So this is the support for the third link. And then over here, we need to define several things. We need to define the Z offset, since this joint is offsetted with respect to the second joint. Or if I go back to the CAD geometry, I have an offset, and this offset is from here to here. And then I need to define axis of rotation. Axis of rotation is the x-axis, and over here I need to define the limit effort, velocity, lower and upper rotational limits, and that's it. And finally, I add the third link. Here's the link file, and I have a small offset with respect to joint 3, and that's it. So let's save this file, and let me now erase this, and let me show you again the file. So this is from line 1 to 29. Here's the second part, and here's the third part. So let's save this. Let's go back over here to the terminals. Let's close this previous RViz simulation. Over here you need to build again everything, and then over here you just need to source again, and then you need to run the launch file. And now we can finally do the final adjustments. So click here on add, find the robot model, click on OK, then click here, expand this and click on robot description, and now all the links are there. So let's click here and select the base link as a start, and here it is. Beautiful. You can see that everything is in the neutral position, and now you can bring up this menu and you can rotate the first link, the second link, and the third link. This looks amazing. And here we are. Beautiful. Okay, now here comes a very important part. Every time you start RViz, you will have to do these several clicks to bring everything. And this is completely unnecessary. That is, we can simply save this configuration. Let's go back here and let's go back to display.launch file, and let's see this file, config.rviz. We need to save the configuration in this file. Not a big deal. To do that, go back to RViz, then click on File, Save Config As, then locate the config folder. So let me now go back. You should go back to the demo workspace. That is the original workspace. Then go to the source. then go to the package, and then find the configuration folder, and then I'm going to save it as config.rviz. Know that this file should precisely match this file name in your launch file. Save it, and let's close everything by going to the terminal, pressing Ctrl+C, and now if you run again, magic will happen, and everything should, okay, so there is an error here. Let me see what is the error. Yes, the error is that this file is not being properly saved. Okay, not a big deal. I'm going to simply close everything and I'm going to repeat. Okay, so the issue over here is very simple since we didn't rebuild everything. So let's press Ctrl+C, go back to the original terminal and then build everything. Then go back here, source again, and then after you run, you should be able to see everything as expected. Very, very good. Okay, that's all for today, and thanks for watching.